Well, now that we briefly looked at how you can measure the spacing between layers, we're going to look at the different ways that these particles can be arranged. And when we talk about a crystal lattice, we mean that pattern, that regular arrangement of atoms in a crystalline solid. And energy drives the formation of this crystalline lattice as it drives so many other things. They arrange themselves in a particular way because energetically that's more stable. It's a lower potential energy. So they're doing this to minimize the energy. So here is an example of a crystal lattice. And if it helps you remember, you've probably seen a garden lattice, right? Where there's slats of wood, little strips of wood going up and down and across, and you have your clematis or whatever growing up this lattice. Well, think of these atoms as being where the bars cross on the lattice. But there's more than one arrangement that is possible. And so we have different ways of describing these lattices. And so we talk about a unit cell. A unit cell is the smallest unit of the crystal that, when you repeat it in 3 dimensions, gives you the entire crystal lattice. So in this example, this is a 2-dimensional example. But if we take this red square and we repeat it in this dimension and in that dimension, we're going to get the intact pattern. If we if we drew something like this, that would give us the right pattern, but it's not the smallest repeating unit that we could pick. Well, this is an example of one pattern, and there are other patterns, and their unit cells are going to be different, but we just have to decide, we have to establish what the unit cell means. I'm trying to think of a different unit cell in here that I could draw, and I'm just coming up with a blank. But in this diagram, the circles represent the lattice points. That's going to be the atom, the ion, the molecule, whatever the particle is. And so this is a cubic unit cell because these unit cells are cubic shaped. They're square here because this is 2-dimensional. The unit cells that we're going to look at, which is not all of them, but in the ones we look at, each atom is the same as other atoms in the structure. We're going to keep it simple. So we're not going to look at one that has like 5 different particles arranged in this really complicated thing. We're looking at carbon atoms. All the atoms are the same. So when we see these pictures, there's going to be different colors. The different colors do not mean that those are different elements. They're just helping us to see what's going on, but all the particles are the same. So we talk about a coordination number, and this is the number of atoms that each atom is in direct contact with. How many atoms is this atom touching on its various sides? So those are the atoms that any particular atom you're looking at can strongly interact with. Like, how many neighbors do you have? The packing efficiency is the percentage of the volume that's occupied by the spheres as opposed to empty space. Because when you pack spheres together, there's empty space, right? And some ways that you can pack them are more efficient than others. If you have a high coordination number, if each particle has more directly adjacent particles, you're generally going to have a greater packing efficiency. There's going to be less empty space. So here's an example of a simple cubic structure. So in this structure we have four different atoms. Let me just jump ahead a minute. Yeah. We're going to look at them in more detail. If we draw a line from the center of each atom to the center of the other atoms, we end up with a cube. And because only part of each of these atoms is within the cube, there's only one atom inside that cube. But each of these atoms is adjacent to 6 others. So if we look at this guy right here, he's got 1, 2, 3, 4, and then there would be 5, 6 that aren't pictured. I think maybe we're just going to come back to this later because this is not the best slide to be explaining all this. Let's just look at this one. So that simple cubic structure, here's where we drew a line from the center of one atom to the center of the next, and we chopped it off. We chopped off the parts that were out of that. If we take this unit cell and repeat it in all 3 dimensions, we will get that structure. Does that make sense? Kind of? Because obviously you can't cut atoms in half or in quarters, right? But this is just representing. And so if we took this one and drew another one right next to it, then here where we're missing part of this atom, it would fill in over here. Whatever the... If you can think of just taking another one of these and setting it right next to this, and you would see that this edge matches up to the edge on the other one. Does that make any sense? Yeah. And so these would be right next to each other, and they would look like a fourth of an atom. And then if you put another block on this side, and one on the top, and one over here, and one over here, you would fill in. This is only part of an atom. But if you put one on the top and on this side and on that side and then filled in the adjacent corner, it would be a full sphere. Okay, she got it. Anybody else? Does that make sense? Kind of? But in this simple cubic cell, these atoms are touching along the edge of the unit cell. And so one of the things we look at is the length of this cube. So the length here is 2 times the radius. The radius is from the center of the atom to its edge. And so here we have 1 r, and there's another radius. And so the length of this cubic cell is 2 times the radius of the atom. This cell has 1 atom in it. It has 1/8 of each of 8 atoms. So this is 1/8 of an atom, and 1/8, and 1/8, and 1/8, and down here there's 4 more 8s, and that all adds up to 1. That make sense? So imagine, we're taking styrofoam balls and we're slicing them. We should get some styrofoam balls and slice them up. Except they're very expensive. They make that horrendous noise when you cut them. Yeah. And little pieces everywhere, right? So here's the simple cubic cell still. So this is what we were looking at. And here we're seeing it within 4 atoms. So we've got 4 atoms here, and we're taking a piece, there's a total of 8 there, 8 atoms. And that's this part in here. Over here, this diagram is showing how it's opening it up a little so we can see what's going on and looking at the coordination number. So if we look at this ball in the center, this atom in the center, how many atoms are touching it? Well, this one, and that one, and this one and that one. So there's 4 in this plane, and there's 1 up here and 1 down there. And so the coordination number is 6. This guy has 6 direct neighbors. Well, for this one, you can look at it as horizontal and vertical planes, but not all of them work very well that way. The packing efficiency is 52%, which means of the volume that the whole structure takes up, 52% of it is atom and 48% of it is empty. So that's not a real high packing efficiency. The body-centered cubic has one atom in the center surrounded by more atoms at each corner of this unit cell. Let's go back to the first, oops, too far. So that's this guy here. So you've got one atom in the middle and 4 around the corners. So it's like you took the simple cubic and you stuck an extra ball in the center of it. That's going to push these guys away from each other a little bit. But that's the arrangement. So here we have the atoms touching diagonally through the cell. These atoms are not touching each other at all. And so to find L, it requires some geometry. So for those of you who like geometry, there it is. L ends up being 4 times the radius of the atom divided by the square root of 3. And remember, this yellow atom is identical to the purple atoms. We just made them yellow so that it's easier to see what we're looking at. How many atoms are within this unit cell? 2. There's the yellow one plus 1/8 of 8 others. You see that? So this one has 2 atoms in the unit cell. So there's the unit cell. If we take that unit cell and put it next to itself and repeat it in all the directions, you start to get something like this. And then to look at coordination number, again, we're expanding it a little bit so we can see what's going on. So here's one unit cell. And what we're going to do is we're going to look at this purple ball, which is in the corner of that unit cell, and see how many other atoms are directly touching it. It's not touching this one, and it's not touching that one. They don't touch along the edge of the unit cell. They touch diagonally. And so this guy is touching 1, 2, 3, 4, 5, 6, 7, and 8. This one's coming out at you. So the coordination number is 8. Higher coordination number. Higher coordination number generally corresponds with higher packing efficiency, and here the packing efficiency is 68%. The last one is 52. So there's less empty space. And these sorts of things actually are interesting to some of the people in Reedley who pack fruit. You know, how do you pack fruit, round fruit, into a box in an efficient way? Face-centered cubic is named because the face has the center of an atom, instead of body-centered, where the center of the atom was in the middle, in the body. Here, the center of an atom is on the face. So face-centered, we've got faces all around, top and bottom, right and left, back and forth. So how many atoms are in that one? 4. Because here's half an atom, and there's half an atom. That's 1. And then there's 2 on the back, 1 on the top and the bottom, and then all those purple ones together are 1. So 4 atoms total. Here we have touching diagonally along the face. Not diagonally across the cube, but along the face. Again, it's not just 2 times the radius, because these guys at the ends aren't touching. And so there's the geometry again, and L is 2 times the square root of 2 times the radius. So there's the cutaway unit cell. Here's how it's fitting into the lattice, and here we're blowing it up so that we can see what the coordination number is. So we're going to look at this guy in the corner, and now the coordination number is 12. That's a little harder to see. but he's actually touching 12 different atoms. Packing efficiency is higher, 74%. Now we get into all kinds of crazy problems. So chromium crystallizes with a body-centered cubic unit cell. The radius of a chromium atom is 125 picometers. Calculate the density of solid crystalline chromium in grams per cubic centimeters. How are we going to do that? If we know the radius of the atom and we know its crystal structure, all of these things we were looking at related the length of a side of the cube to the radius of the atom inside of it. Right? So this is face-centered. They were asking us, though, body-centered. So we need to go back to the body-centered cubic. And the length of a side is equal to 4 times the radius of the atom divided by the square root of 3. So L equals 4R over the square root of 3. Mm-hmm. So L equals 4R over the square root of 3. This is R in picometers. How are we going to find, well, let me back up even further. What is density? Mass over volume. Knowing the radius of the atom and the length of this cube, could we calculate the volume of the cube? Yeah, we could. What would the mass of the cube be? How many atoms are in it? 2, right? Body-centered cubic had that 1 in the middle and the 8 pieces around the edge. So we have 2 atoms per cube. And we know that the radius is 125 picometers. I would rather convert that to centimeters now before I cube it. Does that make sense? We're going to end up with cubic something meters, and we need it to be cubic centimeters. So I'd rather change this now. Changing that to meters is easy. That's 125 times 10 to the minus 12 meters, because pico means 10 to the minus 12. I didn't plan this out very well. So then I need to multiply that by centimeters over meters. And what's the relationship there? Centi means 10 to the minus 2. So I'm going to divide by 10 to the minus 2. So I'm going to end up with 125 times 10 to the minus 10th centimeters. I did that in my head. Let's do it on the calculator too. That's not proper scientific notation either. 125 EE 12 minus divided by 1 EE 2 minus. So that in proper scientific notation is 1.25 times 10 to the minus 8th centimeters. So the volume that we're looking at is going to be L cubed. So we're going to have 4 times 1.25 times 10 to the minus 8 centimeters over the square root of 3, bless you, and that whole thing cubed. So I've got my my radius in there. I'm going to multiply by 4. I'm going to divide by the square root of 3, get that value, and then I'm going to cube it. Are we expecting a large number or a small number? We're expecting a really small number because this is 2 atoms we're talking about. So I'm getting 2.4056, I'm going to carry a couple extras there, times 10 to the minus 23rd cubic centimeters. That's the volume. We need the mass. Well, we need the mass of 1 cube, right? So we've got 1 of these cubes. There are 2 atoms per cube. Do we know what the mass of 2 atoms of chromium is in grams? Well, the periodic table tells us the mass of 1 mole in grams, or 1 atom in atomic mass units. But we don't want atomic mass units, we want grams. So chromium, where'd you go? 51.996. 51.996 grams is the mass of how many atoms? Avogadro's number, 6.022 times 10 to the 23rd atoms. So I've got 2 times 51.996 divided by 6.02 times 10 to the 23rd. And I'm getting a very small number here as well. It's okay. It's good, actually. 10 to the minus 22 grams. I'm going to give up on the bottom of the screen there and go up here. Density is mass over volume. So I've got the mass. That one actually does have 5 sig figs. Well, no, it's got 4 because of Avogadro's number. That many grams divided by the volume. Love the sound of calculator buttons clicking away. How many sig figs does the volume number have? 3. So then our answer is going to have 3. So we've got that guy divided by this guy. So 7.18 grams per cubic centimeter. Is that a reasonable density for a metal? Yeah, metals are more dense than water, right? Water has a density of 1 gram per cubic centimeter. I happen to remember that mercury has a density of 13.6 grams per cubic centimeter. So 7, it's right in there. Any questions? So we looked at these crystal structures by their unit cells. Another way is to look or think of atoms stacking in layers. So the simple cubic cell is 1 layer of atoms in a square pattern with the second layer lined up exactly on top of the atoms beneath. So think about putting marbles in a box or oranges in a box. And so here you're lining up the marbles, and the second layer, this marble is directly on top of that marble. And so the sides are going to be straight, and you're going to have the same arrangement all over the place. That's not the most efficient way, though, and that's not what marbles naturally want to do, is it? If you have a layer of marbles wall to wall in a box and you put some more on top, where do they want to go? They want to go into the little holes, don't they? Oops. No, that wasn't an oops. That was right. So you can get more efficient packing by offsetting the second layer. So here's the first layer, the red. And here's the second layer. And what we're doing is we're moving them over so they're fitting into the dip between these two atoms. And we're moving it down so it's fitting in between these two atoms. And so there's that little indentation here and here and here. And the atoms in the second layer are sitting in those little holes. And so that's going to be more efficient because you can get them closer together. In hexagonal closest packed, you've got the first layer. The second layer is offset so that this guy in the middle is going to sit in this hole. And the third layer is lined up exactly with layer A. That's called hexagonal closest packed, or an AB-AB pattern. This has a coordination number of 12, packing efficiency of 74%. When we look at the unit cell, it's hexagonal. Coordination number of 12. Does that sound familiar? Face-centered cubic had a coordination number of 12. But this one's a little different, isn't it? Here, instead of our cell being a cube, it's a hexagon. This is the smallest cell that can be made, that when you repeat it in every direction, it forms the original structure. So here we've got a layer on the bottom. The layer in the middle is offset, so it sits in the holes. The third layer is directly on top of the first layer. And there's cubic closest packed. So you've got the first layer, the second layer is offset, the third layer is also offset. So this is an ABC pattern. Here we have a coordination number of 12, a packing efficiency of 74%. This is the same as face-centered cubic. The hexagonal closest packed was not the same. This one is the same as face-centered. So here we're using colors to show you the different layers. There's this one's offset, this one is also offset, and then this one's the same again in terms of lining up. If we put those together, tip them on their side, and shave them off, we get this unit cell, which is the face-centered cubic. Pardon me? Yeah, the corners are still an eighth. Each of these on the corner is an eighth, and then we've got halves around the side, and so there's a total of 8 atoms in that cell.